Let's go back to the beginning and let's figure out what a vector actually is. A vector is a physical quantity that has both a magnitude and a direction. What does that mean? Well, it's something that has a size and is moving in a specific direction, something like a velocity, a car that is moving forward with a speed of 65 miles an hour in the northbound lane, so it has a direction on, say, the 15 freeway. Or a plane. A plane could be a two-dimensional vector. It's lifting off from the runway. Therefore, it's not going only in one direction, it's actually moving both forward and upwards during liftoff, so it's at an angle. So it has a direction, a specific angle that it's moving upward, and it has a speed, how fast it's going. So its velocity would be a vector. So a one-dimensional vector would only have one direction of movement, such as north or south or east or west, and it would have a speed, so 55 miles an hour. A plane during liftoff might be traveling at 500 miles per hour at an angle of 53 degrees north of east, or 53 degrees relative to the ground being 0. So this plane, because it's a vector, and it's a two-dimensional vector, has two components. It's both moving forwards and it's moving upwards. So if it's moving at 500 miles per hour at that particular angle, then in 1 hour, it would be 500 miles away from where it started. That would be the straight line connecting the initial position and the final position. But alternately, you could have moved 300 miles per hour forward for 1 hour and then 400 miles per hour straight up for 1 hour, and you ultimately would have ended up in exactly the same position. So, you guys are already familiar with this. You have seen this before. You've drawn a line on an X and Y graph, and you've referred to a point with an X and a Y component. You've said this is 3 forward and 4 up. So the X component is 3 and the up component or the Y component is 4. Now instead of referring to it as X and Y on an XY graph, now we're going to refer to it as its distance or its length from its initial position. So this vector would have a length of 5 at an angle of 53.1 degrees, and it would ultimately end up in exactly the same position as if you went 3 forward and 4 up. Now please realize this is one thing, this is one quantity such as a position or a velocity. We're not using our triangle to solve for something else. We're taking what we already know and we're reducing it into two different components, because we can never consider two directions as one thing. We can talk about it as one thing, but our equations work differently in the two different directions, in the north and the east, northeast, or if it's up or down, or forward or up. Okay, those directions are always going to have to be considered separately. So how do we consider them separately? Well, we do what's called resolving two-dimensional vectors, known as breaking a single vector. Remember, this is one quantity. We're breaking a single vector down into its directional components. We're not using this triangle to solve for anything. We're simply taking one thing and breaking it apart into its two different parts. So let's start with a velocity vector, and this velocity vector is moving upwards at an angle of 15 degrees at 25 meters per second. Now, we know that when you toss a ball in the horizontal component, that acts like the constant velocity model, versus in the vertical component acts like the constant acceleration model. So we actually have to consider the horizontal and the vertical components separately. So we need to know what portion of this velocity is being used to go forward and what portion of this velocity is being used to go upwards. And we call that the X component and the Y component. And we have this handy dandy thing that we were taught in geometry called SOHCAHTOA. And that tells us that if you draw a triangle, you can figure out the sides of the triangle. If you know the hypotenuse in one angle, even any just one side in any one angle, you can use SOHCAHTOA to find the other sides as well as the angle. So let's start with the Y component. Well, the Y component is opposite to the angle. So the sine of theta is equal to the opposite over the hypotenuse. That's our SO. So sine of theta in our particular triangle, that Y component is the Y component of this velocity, so I'm calling that Vy, and this Diagonal component is our total velocity, or our v total. So to solve for Vy, we move that V over to the other side, and we get Vy equals the total V times the sine of the angle. And I plug that in, our total V is 25, and our angle is 15, so 25 times the sine of 15 equals V. And we put that into a calculator, and we get that the y velocity, or the vertical component of this velocity that's making this object go up, is 6.47 meters per second. Now, I want you to realize that every single time you do this, you must start from here. You may not just assume that the y component will always be the sine. It won't. Sometimes it will be different. You must always start by looking at the triangle and seeing what is opposite and what is the hypotenuse, and realizing which of these you have to use. Now, let's look at the x component. Well, in this particular case, the x component is next to or adjacent to the angle. The y component was opposite, it was facing. The x component is adjacent, and we know the hypotenuse. So the one we're going to use is cosine. Remember, I told you, if you can, always try not to use something you've already calculated. We've already calculated this, so technically we know this, and we could use tangent, but that would rely on us having done this correctly, and there's no guarantee that we actually did that correctly. So always start with something like cosine, which uses the givens, or what was given to you that you absolutely know is correct. So the cosine of theta is equal to the adjacent over the hypotenuse, that's our ca, so ca. Okay, our cosine of theta in this particular one is the x component of the velocity over the total velocity. So I move that total velocity over, and I get Vx equals V times the cosine of theta, and I plug that in with 25 as our total velocity times the cosine of theta, and I get 24.15 meters per second. So now I know that my components here, okay, are 24.15, and my component here is 6.4. So this would be the same as what you guys did in math, as marking this position as 24.15 meters per second in the x, and the y would be 6.47 meters per second. So if we drew an imaginary xy graph on here, this component would have this position on it. That would be our x, and that would be our y. Let's double check that and make sure that that's absolutely correct. We know that if we have two sides of a triangle, we can get the third side using the Pythagorean theorem. So a squared plus b squared equals c squared, or the hypotenuse is going to be the square root of a squared plus b squared. We plug in the values that we found, we double check it, and we get 25. So we know that we broke down or resolved this particular vector into its components correctly. A hint: you will never use tangent when breaking down or resolving a vector. When you're breaking down a vector, you will use sine or cosine. What about putting a vector back together? Well, a vector that you put back together is called your resultant vector. Adding two or more vectors in perpendicular directions together will get you a result, or a resultant vector. So let's say that somebody travels, let's say we have a truck driver and he's going to make a delivery, and he travels 12 meters east and 5 meters north. And we want to know how far he really is from the place where he started, or the factory where he picked up the furniture that he was going to deliver. And the shortest distance between 2 points is always a straight line. So that's going to be that diagonal vector is going to tell us exactly what his total change in position is. And it's going to tell us what his current position is. So to get the vector magnitude, well, we know two sides, and we know that the easiest way to get the third side of a triangle is Pythagorean theorem again. A squared plus b squared equals c squared. So c is equal to the square root of a squared plus b squared. So in this particular case, that's 12 squared plus 5 squared, square rooted, is equal to c, which is 13 meters. So this vector, he is actually 13 meters from where he started. Okay? Now, remember from the very beginning, from the very first board, a vector has both a magnitude and a direction. So we need to know what direction he actually is from where he started. So to get the direction, this is where we have to go back to our SOHCAHTOA. This time, our givens are the adjacent to the angle. So we're going to say our angle is here. Yes, we could have used the angle here if we had wanted to. I'm going to go ahead and find this angle theta here. Okay? We now know both sides of the triangle, so that's the adjacent and the opposite, so the one we want to use now is tangent. And again, another hint, whenever you're adding two vectors, you're always going to want to use the tangent. So breaking vectors down is the sine and the cosine, putting vectors back together is the tangent. So the tangent of theta is the opposite over the adjacent. So the tangent of theta in this particular, so we want to find the angle, so the opposite of the tangent is the inverse tangent, so we would take the inverse tangent of both sides, and that would give us our theta. Our inverse tangent cancels with our tangent, and we end up with theta is equal to the inverse tangent of the opposite over the adjacent, which in this case, the opposite to the angle or across or facing the angle is 5, so that's 5, and the adjacent or next to is the 12, so theta is equal to the inverse tangent of 5 over 12, and that tells us that this is 23.6 degrees, and it is north from east, or upwards from the east. We are saying that east is the 0. So this flat east would be 0, and he's up north of that, so the angle would be 22.6 degrees north from east. So I hope that helps you guys with resolving vectors.